In our previous YouTube video, Micro Introduction to AM, episode 1 and 2, we have explained about the additive manufacturing process. This process is very useful for manufacturing of complex metallic parts, and we showed some ways how to improve the part shape and how to simulate the building process. In the selective laser melting, the basic process parameters include the thickness of the powder bed, laser spot size, laser power, scanning speed, and the distance between the scan tracks. To create a dense part, we combine the process parameters so that we build continuous tracks. In addition to this, the scanning strategy has also a lot of impact on final part quality, as it can be scanned in different ways. For example, simple zigzag lines, by strips, or by rectangle, or hexagonal island, or some other strategies. Many physical phenomena occur during the laser powder interaction. We use laser beam as the heat source to melt the metal powder, but a large amount of applied energy is reflected by the powder. The absorptivity for metals is usually between 0.2 to 0.8, which means 20 to 80% of the energy delivered is absorbed depending on the metal. Depending on the local heat transfer conditions, behavior of melting changes from insufficient melting to optimum melting until overheating mode. Both insufficient melting mode and overheating mode leads to porosity, which reduces the mechanical property of the parts. To minimize or to avoid this problem, better understanding on the relationship between effect of process parameter with final part quality is required.
The parts produced by SLM process have typically a low surface quality, mainly because of the interaction between the tracks and projections of metal droplets from the melt pool. To reduce their surface roughness, they usually need to be post-processed, most often with machining tools or laser. Mechanical grinding is one of the conventional post-processing methods. It is an abrasive machining process to improve the surface finish of the parts. However, the use of conventional post-processing methods is challenging for small components and especially components with delicate features or thin walls. An alternative post-processing method to reduce the surface roughness is, for example, laser polishing. It is a rapid laser post-processing technique based on the principle of remelting the material surface of the component with a laser. Continuous or pulsed laser beams with high energy levels are used to irradiate the material surface. The interaction between the laser beam and the material surface leads to partial evaporation or remelting of the material. As a result, due to combined effect of surface tension and gravity, the melt pool is redistributed to a horizontal level, which reduces the surface roughness. Laser polishing can be used for post-processing of complex shaped and smaller parts compared to the conventional mechanical post-processing techniques.